Alrighty, so we're going to start a new section here, it's, section 7.8. This section will not be on your first exam, it will be on your second exam, which is actually 2 weeks from your first exam, so make sure you have that date down. So the topic of this section is the improper integral. And so what this is going to mean is we're going to be dealing with integrals that involve or that contain infinities now. So the entire subject of this chapter is integrals involving infinities. And there are two types. So type 1, we have infinite intervals. And so what that's going to look like is, so if you imagine, so the example that gets used is, if you imagine, y is equal to 1 over x squared. So let's only look at that in the first quadrant there. So what that's going to look like is something like this. I might be interested in finding, the area, starting from here all the way down this axis. So keep going, and the question is, is that something I can do? Does that make sense to do? Will I get something? Will I get a number? Will I get something that's divergent and going off to infinity? And the question is, the answer is, whether or not you get a number depends on your function. So let's take a look at what this integral is, and let's go ahead and call this point 1 here. So let's consider this integral. So we have the integral from 1 to t of 1 over x squared dx. And so I can do this integral. So t is, t could be any point along this axis here, to the right of 1. So if I do this integral, I'm going to get negative 1 over x evaluated from 1 to t. And this ends up being, when you evaluate it, 1 minus 1 over t. And so if you look at this thing, this term, you can already see as t gets really large, that term is going to 0, the 1 over t term. So then I can, say that, I can then say that, this area that I want to find, so the area in red, we could define it to be, so let's call this A of t. So this A of t, just describes the area underneath 1 over x squared up into the point t. So you can plug in different values of t and get different areas. So the area in red, along the entire x-axis there, is going to be the limit as t approaches infinity, we'd like it to be, and so we're going to define it, of A of t. And so we've already, determined what A of t is. This is the limit as t approaches infinity, 1 minus 1 over t. First term's constant, so, we can ignore it. Its limit is what it is. It's 1, and the second one, as t goes off to infinity, that's going to 0. So this area ends up being, we were able to calculate it to be 1. So that kind of gives us a way to define these areas. So we're gonna make the definition that the integral from 1 to infinity, 1 over x squared dx, we're going to define this to be the limit as t approaches infinity, the integral 1 to t, 1 over x squared dx. And in this case, it ends up being 1. So this is actually kind of profound, if you think about it. I take, something that has an infinite length here. I'm thinking about these, so think about these in terms of Riemann sums. I have these rectangles that I'm adding up an infinite number of those areas, and I'm getting, 1. And that's that's actually really cool. You wouldn't exactly expect that. Okay, so let's write down the actual definition. This was, the definition for 1 over x squared. So the definition of an improper integral of type 1. So this is, the infinite interval. So A. So we're going to have three different definitions. So one's going to be, if it's going off to infinity, one's going to be off to minus infinity, and the other is going to be um, if it's negative infinity to infinity. So we say if the integral from a to t f of x dx exists for all t greater than or equal to a, then we write the integral from a to infinity, and we'll talk about this definition in a minute, what it really means. F of x dx is equal to the limit as t approaches infinity, the integral from a to t f of x dx. And so what this is saying is, if I have this integral right here, integral from a to t f of x dx, if, no matter what t I plug in, I get something finite. So I could plug in t equals 1, t equals 10, t equals 100, t equals 1,000, keep going. And as long as I keep getting, numbers that aren't going off to infinity, so as long as this integral exists, then I can, evaluate this integral by first, so I can, evaluate the integral from a to infinity by first finding the integral from a to t, and then evaluating the limit. And this is really important. So one of the things that you're going to get points docked off for is if you try and evaluate, if you try and evaluate this thing at infinity. What I mean by that is like drawing the line after you find an antiderivative and writing a and infinity up there. Again, infinity is not a number. It's the idea that, no matter how far out you go, there's still something further. So you don't want to evaluate things at infinity. You want to find these limits. So just be careful of that when you're presenting your work. You will lose points for trying to write like 1 over infinity. That's not a number. Yeah. So just again be careful with that. Let's go ahead and move on. So we have something similar. So if the integral from, in this case, we have t to b f of x dx exists for all t less than or equal to b. So this is the opposite case now. I can pick smaller and smaller numbers, going off to negative infinity. Then we can say that the integral from minus infinity to, I'm using b in this case, minus infinity to b, f of x dx is equal to the limit as t approaches negative infinity, the integral from t to b, f of x dx. Again, all this is saying is, instead of, if I want to evaluate an infinite integral or over like an infinite interval, all I do is, I use a variable, and then send that variable off to infinity after I integrate. And then, so we need to add one note, provided this limit exists and is finite. So we need to add the same note up there. I dropped that. So, as long as you're getting something finite, we'll define it to be that. If you get an infinite number, we just say it diverges. Okay, so yeah, so that's the next one. So I'll finish off this definition. I think this will be the end of this video. So the improper integral is, so the integral from a to infinity f of x dx and the integral from negative infinity to b f of x dx, improper integrals, are called convergent if the limit exists And of course, you can probably guess uh, what they're called if it doesn't exist. So they are divergent if the limit does not exist. This can mean going off to infinity or negative infinity. Um, that's typically what we'll mean when we say divergent. You could have something. You could have some other situations that we're not going to get into, and if we see them, we'll cover them. Um, but there's one last part to this. So if the integral from a to infinity f of x dx and negative infinity to a f of x dx. So if I integrate off in both directions, and these are convergent, then this integral, so we'll define the integral from minus infinity to infinity f of x dx. We'll define this to be the integral from negative infinity to a f of x dx plus the integral from a to infinity f of x dx. And so, so what you should know with this is so first two make sense. Third one, you have to, so you want to be careful with this one. So this is the definition we're going to take. What you don't want to do is you don't want to replace those infinities with a negative t and a positive t, and then take the limit. That's something completely different. So if you go on to higher maths, there's a name for that. We're going to define it to be, I split it up into two integrals. So just know this definition, be aware what it means, and know how to do this. So I'm going to stop here, and I think we're going to jump into examples. We'll also talk about, we'll have other types of improper integrals. So